So calorimetry is what we're doing today. Calorimetry. And that means measuring calories. So calorimetry is a type of experiment where we are examining heat transfer, and we could calculate specific heat capacities, or we could do all kinds of things. So the general idea on this is we use a calorimeter, and calorimeters can be very, very fancy, or they can be very, very simple, like the styrofoam cups we're going to use today. So we have a styrofoam cup. Styrofoam because it's insulating, okay? And what we'll do, there's a couple of different ways it can work out. But what typically happens is that you've got some cold water in your calorimeter, and you know what temperature it is. So you have an initial temperature for the cold water, and you have a mass of the water, and you know the specific heat capacity of the water, which is 1 calorie per gram degree Celsius. And then what you do is you take a piece of metal or whatever you're studying that's hot, and you stick it in the cold water. Hot piece of matter. So that piece of matter has an initial temperature, and it has a mass, and maybe we are trying to find the specific heat capacity, because this is how you would determine the specific heat capacity. So we don't know what C is. What's going to happen to the temperature of the cold water? Is it going to go up or down or stay the same? It'll go up because we put something hot in it. And the temperature of the metal is going to go down. And are they going to end up at the same temperature or different temperatures? They'll end up at the same temperature. So the final temperature, maybe we'll make that green. The final temperature will apply to both the water and the metal. Oh good, that disappeared. So because heat will transfer based on a temperature difference. And so the metal cools down, the water heats up until they get to be the same temperature, and then everything just stays the same. Well, assuming that the calorimeter is a good one and we're not losing heat to the outside, we can have two different equations. Remember, the Q equals MC delta T was our basic equation. So for the water, the amount of heat that is gained by the water will equal the mass of the water times the specific heat capacity of the water times the change in temperature for the water. Well, the change in temperature for the water is that final temperature, which is common to both, minus the initial temperature of the water. We also can do this equation for the hot object, the metal. So Q equals the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. So in lecture we looked at just these two things separately. And here the temperature change for the metal is again going to be that final temperature, which is the same for both of them, minus the initial temperature of the metal. Where did the heat come from to warm up the water? It came from the metal. And assuming that there's nothing being lost, which is not technically true, but we're just going to be simple about it. So we're going to assume that no heat is lost to the environment, that all the heat stays inside the calorimeter. Any heat lost by the metal must be gained by the water. Law of conservation of energy. Energy is not created or destroyed. So what that tells us is that, let's get the colors right here. The heat that is gained by the water must equal the heat that is lost by the metal. And when we use signs in terms of energy, that's referring to an exothermic, endothermic type process. The water temperature went up. That means that energy came in. When money comes into your wallet, do you feel positively or negatively about that? Positive. I like it when I get more money in my wallet. And when money leaves your wallet, even if it's for something that you really, really wanted, you still have that twinge. Like, oh, there goes my money, right? It's negative. When energy leaves something, we give it a negative sign. So here, the energy being gained by the water must be equal to, but opposite in direction, to the energy lost by the metal. Okay, so this gives us another relationship. We've got this one, and we can solve this for Q because we know M and C and delta T. And over here, now we can find this Q because it's the same as this Q with the sign changed. And we know the mass, and we know the change in temperature, so we can solve for the specific heat capacity. Question?
So that means automatically that the Q is going to be negative on the metal?
Yes. And that is because of how delta T is defined. It's the final minus the initial.
So it's just mirrored?
Yeah. So for the metal, the initial temperature was high. Maybe it was, 100 degrees because you heated it up in boiling water. And then it cools down to 50 degrees. Well, the final temperature, 50, minus the higher initial temperature is going to give you a negative number. And so it's in experiments like this where the negatives become important. Okay? So this is the basic idea of what we're doing in lab today. Any questions? The individual equations are not complicated. What is a little bit tricky is just understanding what the heck are we doing here, which is what I'm trying to explain to you right now. We've got heat leaving one substance and coming into another. And if we know all the variables but one, we can solve for that one variable.